So up to now we have spent a chapter and a half, or chapter and 3/4, on acid-base reactions. But in chapter 4, when we first learned about acid-base reactions, we also learned about another reaction, precipitation reactions. Precipitation reactions when you have two soluble compounds come together in aqueous solution and one of the products is insoluble, so it precipitates out of the solution. We determined what precipitated out using solubility tables, which tells us if it contains this ion, then it's going to be generally soluble unless you have these exceptions, in which case it is insoluble. And we just defined insoluble is something that does not readily dissolve in water. But what we're going to find is all of those things back in chapter 4 that we said, okay, these things are not soluble, actually do dissolve to some small degree. Almost all ionic compounds do dissolve in water to some degree. It just may be a very, very small degree. And that's what we're going to determine today, is what exactly is that solubility. So we're going to do this through an equilibrium reaction. So the equilibrium reaction says that I'm going to go from the solid state to the aqueous state. Now, when an ionic compound dissolves in water, it also dissociates. What do I mean by dissociates? What does that mean for an ionic compound to dissociate? Breaks apart into the ions. So we're all familiar with the sodium chloride breaks apart. You get sodium plus ions and chloride minus ions. We're going to do that for things that are generally less soluble, so they're only going to do to a small degree or to an equilibrium. So because it's to equilibrium, we're going to have an equilibrium constant. So that's always an uppercase K. So uppercase K, but now our subscript is going to be SP. SP standing for solubility product. So this is still an equilibrium constant, works the same as all the other equilibrium constants, but now it's specifically for a solubility reaction or for the equilibrium of a dissociation reaction. So the solubility product constants will allow us to determine exactly how much of this ionic compound should actually dissolve in water. So that's our KSP. So here is a compound that, according to our rules back in chapter 4, is insoluble, silver chloride. According to our rules back in chapter 4, chloride ion-containing compounds are generally soluble, but we had a couple of exceptions. One of them are those that contain the silver ion. Silver ion we define as insoluble, but it does dissociate to some small degree, and we're going to show that using our equilibrium arrows, that it does to some small degree dissociate in water. Now, because this is 1-to-1, we have our K equilibrium expression is equal to the products over the reactants. Why do I not have anything in the denominator here? Why is there nothing down there? Good, because our reactant is a solid. Solids don't exist in equilibrium expressions. So we're just going to have the product of our two the product of the products there. So the silver ion and the chloride ion, which are 1-to-1, so these have powers of 1. The smaller the K, we learned back in chapter 15, small K's means that the reaction proceeds very, very little towards the product. So if we have a small KSP, that means majority of it is going to stay over here on the reactant side, and very little of it's actually going to dissolve. So large KSPs are things that dissolve more, small KSPs are things that dissolve less. So there's two different numbers we can calculate to go along with this idea of how much dissolves. One is the molar solubility, and the other one is just the solubility. So same idea, the difference just is the units here. So molar solubility is the number of moles of solute in 1 liter of a saturated solution. Moles per liter, which is the exact same thing as molarity, moles per liter. Now, the issue with that is that we're dealing with things that are very, very low solubility, so they're going to have a very, very low concentration. So molar solubility for these things is usually going to be a very, very small number. So a more useful number used often is just the solubility. Solubility is how many grams dissolve per liter. So it's the same idea, we're just going to use grams in the numerator instead of moles. Now, again, how do we convert between moles and grams? What do we use to convert between moles and grams of a compound? That's to go between moles and atoms. How do we go from moles and grams, though? The mass, the atomic weight, the sum of the atomic weights for the compound. So to go from moles to grams, we multiply by the molar mass. If we were going backwards from grams to moles, we divide by the molar mass. And the molar mass is the sum of the atomic masses. Now, for the purposes of simplicity, we're going to do all of these assuming room temperature water or 25 degrees Celsius. Obviously, some things we are aware of as you increase the temperature, generally increases the solubility of a lot of different compounds. So we're just going to focus on everything at 25 degrees Celsius to make it even across the board. So how do you go about determining the solubility? Number one, construct an ice table. We have an equilibrium reaction, so we can do an ice table to determine what the concentration of the ions is at equilibrium. So let's say, for example, I want to know what is the molar solubility of silver bromide. And I know I'm given that the KSP for silver bromide is 7.7 times 10 to the negative 13. Is that a relatively large K or relatively small K? Small K. So generally, we would consider this generally an insoluble compound. It's only going to dissolve to a very small amount, so we're going to expect a very low number for its molar solubility. So we make our ice table. First part of the ice table is our equilibrium reaction. So silver bromide dissociates into silver ions and bromide ions. We're going to completely ignore the silver bromide column. Why? It's a solid, so it doesn't affect the equilibrium. We're starting off with 0 for both our products here. Now, instead of using X, we're just going to use S. Works the same way. It just S is going to stand for our solubility. So plus S and plus S, S and S. So if we were to write out our equilibrium expression here, K would be equal to what? S squared, good. Because it's going to be equal to the silver ion times the bromide ion. So in this case, KSP is equal to S squared. This KSP we were given to be 7.7 times 10 to the negative 13. So how do we solve for S? Square root of both sides. So take the square root of both sides, and we get that S is equal to 8.8 times 10 to the negative 7. Now, everything inside of an ice table is always in units of molarity, so we're already at molar solubility, and we've answered the question. This is our molar solubility here. If I wanted to have the solubility, instead of the molar solubility, to go from moles to grams, again, we multiply by the molar mass. So we would determine the molar mass of silver bromide and just multiply our answer by that. As you can see, that's a really small number, 10 to the negative 7 molar. Very, very low concentration. So let's go ahead and convert that to a normal solubility in grams per liter just to see how it's done. So we multiply by the molar mass. How are we going to determine the molar mass? How do we find the molar mass of silver bromide? Look at the periodic table. So look at the periodic table. Silver has a mass of 107.9. grams per mole. And bromine has a mass of 79.90 grams per mole. There's only one of each, so we just add them up, and that gives us 187. Yeah. 187.8 grams per mole is the molar mass. So if I take my molarity, again, molarity means moles per liter, and I multiply by that molar mass, 187 grams per mole, what unit cancels? Moles. Moles cancels, and I'm left with grams per liter. So multiply by that molar mass, and we get 1.7 times 10 to the negative fourth grams per liter. So if I were to dissolve this compound, 1 liter of water at room temperature could only hold 1.7 times 10 to the negative fourth grams. That is less than a milligram. That is a very, very small amount that actually dissolves. Which is why we generally would consider silver bromide to be insoluble. Only a very small amount dissolves. And questions about how to determine the molar solubility and the solubility. Not that bad, right? So in this last problem, I gave you KSP, but where did KSP came from? Well, just like our KAs and our KBs, it's going to come from a table. So on page, oh, I don't think they have it on the slides, do they? No, they don't. Okay. On page 803 of your textbook here is a big long table of solubility product constants right here. Page 803, and it continues on to the top of page 804. Page 803 to 804, table of solubility constants. So when you're working on these problems and you need to know what is the K value for any particular ionic compound, it's in that table. Now, they are in order, in alphabetical order of the name, not necessarily the formula. So for example, silver bromide is under S for silver, not A for Ag. So when you're looking at that table, it's in alphabetical order of the name. Let's try this out. Calculate the solubility of copper 2 hydroxide in grams per liter, so the solubility. So if I'm looking at this table on page 803, copper 2 hydroxide has a KSP value of 2.2 times 10 to the negative 20. So that was from the table on page 803. Now, the next thing we need to know is we need to know what is this dissociation reaction going to look like. So copper 2 hydroxide, when it dissociates, we get a copper 2 plus ion, and then we get 2 hydroxide ions. It's important to make sure your dissociation equation is balanced, because does stoichiometry play into your ice table? Does it matter that I have 2 hydroxides instead of just 1? Yes, it definitely matters. It matters both in the ice table and in writing the equilibrium expression, because equilibrium expressions contain stoichiometry. So when I go to write the equilibrium expression, it's the products, so copper and hydroxide, but I have 2 hydroxides, which means I'm going to square the hydroxide when I write my equilibrium expression. So the stoichiometry is going to affect it in 2 different places. Number 1 in the equilibrium expression, number 2 is going to affect it in the ice table. But you understand why that's the equilibrium expression before I go ahead and make our ice table. All right, I'm going to close this so I can open a new blank slide to make our ice table. there's our equilibrium reaction. We make our ice table. And we're going to ignore our solid reactant. Starting off with a 0 for both of our products. In our change column, what's going to go in our change column right here for copper? Plus S, good. What's going to go in our change column for hydroxide? Good, plus 2S. Again, because there's 2 of them, so we need plus 2S there. So that's going to be S, and that's going to be 2S. Again, let's remember our equilibrium expression is equal to the copper ion times the hydroxide ion squared. Now let's plug in what we know. So KSP we found in that table on page 803 to be 2.2 times 10 to the negative 20. Copper we now have defined as S. Hydroxide we've defined as 2S. Don't forget that that's still being squared. Yep, the table on page 803. So what does the product side here simplify down to? Good, 4S cubed. Does everybody understand where we got that from? All right. Now we can divide the 4 over to the other side to get rid of it, and then take the cube root of both sides. Where did my good calculator go? And I'm getting 1.8 times 10 to the negative 7 for my S. Again, divide by 4 and then take the cube root. Not square root, cube root. Everybody know how to do a cube root in their calculator? Okay. So what is the unit here for S? Molarity. But the question asked us for what unit? Grams per liter. So what do we still need to do with this molarity? Good. Multiply by the molar mass. The molar mass of copper, 2 hydroxide, you add up copper, 2 oxygens and 2 hydrogens. Save us time. Let's go ahead and use the 97.57. Grams per mole. Moles cancel. And we get 1.8 times 10 to the negative 5. And now we're in grams per liter, and that is our solubility. So yes, we're still doing ice tables, but it's not as bad as the titrations. The main thing is keeping track of the stoichiometry here.
Wait, you're multiplying by molar?
Yes. So that molarity is technically moles per liter. So when you multiply by the molar mass, moles cancel, and we're left with grams on the top and liters on the bottom. All right. Let's try this in reverse. All right, so how do we determine these KSPs? We're going to determine the KSP from the concentration of a saturated solution. How do you know the solution is saturated? How can you determine a solution is saturated? What is the definition of a saturated solution? Chapter 13. Good, when it won't dissolve anymore. So I take the solid, I put it in the water, I stir it up, and I keep on adding more solid until it stops dissolving anymore. Once it stops dissolving anymore, I know it is now saturated. So let's say, for example, calcium sulfate. We saturate a solution and we measure that the concentration of it is 0.67 grams per liter. A couple of different ways of measuring that concentration. If this was a colored compound, we could use Beer's law, just like we did in the lab a couple of weeks ago. Let's go backwards, and from this solubility in grams per liter, determine what the KSP is for calcium sulfate. So we're starting with the solubility going backwards. So exact problem we just did, but going backwards. So the very first thing we need to do is take that solubility and get it into a molar solubility. So we're taking grams in our solubility here, going back to moles. So how do you go from grams to moles? Divide by the molar mass. Good. So first of all, we're going to take this solubility, we're going to divide by the molar mass. So molar mass of calcium sulfate, if you add up a calcium, a sulfur, and 4 oxygens, is 136.2. So we do that, divide by it, we get 4.9 times 10 to the negative third moles per liter, and that is our S. Next thing we need to do is plug that S into our equilibrium expression. So calcium sulfate when it dissociates, we get calcium ions and sulfate ions in a 1-to-1, like that. So if I were at the equilibrium expression for this, it would be the calcium ions times the sulfate ions, 1-to-1, so we don't have to worry about any powers. Now you could do an ice table if you wanted to here, but if we did an ice table, it's 1-to-1, it's pretty obvious to see. Both of these are going to end up being S. S times S. So KSP is going to be S squared. Again, you can do an ice table if you want to confirm that. But all we need to do now is plug in the S we found. The 4.9 times 10 to the negative third molar, so square it. And we get 2.4 times 10 to the negative fifth. Again, K's have no units, so we leave off the unit there. That's a relatively large KSP unit. Yes, I know 10 to the negative fifth sounds small, but compared to the last one we did that was 10 to the negative 20, that's pretty big. So compared to most of the things on this table, most of the things that we would generally consider insoluble, calcium sulfate is pretty high on the solubility range. So do we feel like we could find the solubility, molar solubility, or use this molar solubility to go back and find KSP? Not that bad. All right. Moving forward. Reaction quotient, back to chapter 15. What was the difference between K and the reaction quotient? The formula for them was the exact same thing, concentration of products over concentration of reactants. So what was the big difference between Q and K? Determines if the reaction is going forward or backwards, depending on whether or not it was bigger or smaller than K. So the big difference is with Q, it doesn't necessarily have to be at equilibrium. The formula is the exact same formula, just with K, we know we are at equilibrium. If we're not necessarily at equilibrium and we calculate it concentration of products over concentration of reactants, that means that we just may not be at equilibrium, and that would be our Q. We can use Q with solubility to try and determine at what point we're going to start making a precipitant. So what I mean by this is at what point we're going to start having a precipitation come out of solution. So precipitation means that it is no longer soluble. If I react two different things and the product is insoluble, but I react such a small amount that the product that's produced is still below its solubility, nothing will precipitate out. I won't see anything yet. So a lab, for those of you who had me for a CETA lab last semester that we did last semester, was families of elements. And in that case, we had the chem plate with the 12 different Wells plates, and we were varying the ratio of the two reactants to figure out which one gave the most solid precipitant. Now, the ratios on either side that was very, very small ratios, you probably didn't see any precipitation because you probably produced so little product that it was below its solubility. So you would have seen no precipitation. So that's what we're trying to do here, is determine at what point we start to see a precipitation in one of these reactions. So let's look back at the silver chloride, which was actually one of the things that back in the lab on families of elements, silver chloride was one of the solids that we formed. Q, again, calculated the exact same way as K, concentration of products over concentration of reactants. So in the case of silver chloride, it would be silver ion times chloride ion. If Q is less than K, then we haven't reached the point where we're going to see a precipitation. In other words, we haven't reached that solubility yet. The small amount of silver chloride that's formed is still going to be able to dissolve because we haven't reached this top maximum solubility yet. If Q is greater than K, then we will now see a precipitation form. And then I just means whatever its initial concentrations were. So let's try this out. For the following solutions, we're going to predict whether or not a precipitant will form when I add them to 650 milliliters of 0.008 molar potassium sulfate. Now, so the first thing we're going to need to do is determine if a precipitation forms, what is it that's being formed that is insoluble? So let's look at the very first one. We are reacting potassium sulfate with barium chloride. Back to chapter 4, how do you predict the products of a precipitation reaction? I'm reacting those two things together. I'm going to switch, right? So potassium is going to leave sulfate and go with who? The barium or the chlorine? Chlorine. And the barium is going to go to the sulfate. So we'll end up with potassium chloride and barium sulfate. Which one of those is insoluble? Potassium chloride or barium sulfate? Barium sulfate is insoluble. So the insoluble product that is formed here is going to be the barium sulfate.
That's because it's in the metal group, right?
No, potassium's a metal also.
That's
It's because of the rules back in chapter 4 says barium sulfate would be insoluble while potassium chloride would be soluble. The very first rule in the solubility tables is if it contains a group 1A or 2A metal or ammonium, it is soluble with no insoluble exceptions, which means potassium, which is a group 1A metal, anything it's with is always going to be soluble. So that's a quick and easy way for a lot of these, well, all of them, because potassium is what we're reacting all of these with. Whichever one potassium ends up with is going to be the soluble compound, so the other thing must be the insoluble. But you can always double check your table of solubilities back in chapter 4. So barium sulfate. If I look up barium sulfate in the table on page 803, I find barium sulfate has a solubility constant of 1.1 times 10 to the negative 10. So if that's K, I need to find Q in order to determine whether or not it precipitated out. So to find Q, I need to find out what is the concentration of the barium ion and the sulfate ion. So the concentration of the barium ion is going to come from my 250 milliliters of 0.004 molar barium chloride. All right. So how do we go between the molarity of a compound to molarity of just the ion? Molarity of a compound to molarity of an ion. Get a blank page real quick and we'll just do quick examples from chapter 4, see what we remember. All right, so let's say I am 0.20 molar sodium oxide, sure, sodium oxide. What would be the concentration of sodium ion in that solution? When sodium oxide, which is soluble, dissolves, I get how many sodium ions? 2 sodium ions and 1 oxide ion, right? So what's the ratio, molar ratio between sodium oxide and sodium? 2 to 1. So what would be, if I'm 0.20 of this, then what would I be of that? Are we overthinking it? All right. Let's do it as a molar ratio. 0.20 sodium oxide times molar ratio. What goes on top? I'm trying to get to which one? Sodium. What goes on the bottom? Sodium oxide. What is that ratio going to be? What over what? 2 to 1. 0.4. Remember that now? So it's 0.4 molar sodium ion. What molar of oxide ion would it be? 0.20, good, because that one was 1 to 1. So finding the concentration of an ion from its original compound is just multiplying by the stoichiometry. Remember that now? All right, let's go back to our problem. So in our problem, if I am 0.0040 barium chloride, then what concentration would that solution be of barium? Barium. What's the ratio of barium? 1 to 1. So it would also be 0.0040 molar barium ion. Therefore, I can ignore the chlorine and just say I'm 0.0040 molar barium before I mix the solution. Now, what do I mean before I mix the solution? I have 250 milliliters of it, and I'm adding 650 milliliters of the new solution. Yes, there's other stuff in that solution, but I need to know what is the concentration of my final solution. So technically what I'm doing here is I'm diluting it. How do we calculate the concentration of a dilution? What equation? What equation tells us the concentration after we dilute something? Again, still going back to chapter 4. Look familiar? M1V1 equals M2V2? Yes. So the molarity before the dilution times the volume before the dilution is equal to the molarity after the dilution times the volume after the dilution. So let's first of all, for barium, find out what its concentration is after we dilute it. Let's do it first for barium, and then we're going to have to do the same thing for sulfate. Figure out what the concentration is of the sulfate ion. All right, so let's actually clean off this board and use that one. So we have 250 milliliters of 0.0040. Point 0040. And my initial volume was 250 milliliters. M2 is what we're solving for. What will be my final volume?
650 plus 250.
Yep, 650 plus 250, which is what? 900 milliliters. Good. So the concentration of my barium ion is equal to what? We're diluting, so it should go down. So it should be something less than 0.0040.
0.001.
Good. 0.0011 molar. So that's my barium ion. Now let's find our sulfate ion, because that's the second part here is the sulfate. So we're going to do the same thing for the sulfate. So sulfate is also 1-to-1. So we can use the molarity of it times its initial volume. So its molarity is 0.0080. Its initial volume was the 650 milliliters. And after mixing, we had 900 milliliters. So the concentration of sulfate is what? I'm getting 0.0058. Molar. So the KSP for this, we found again on the table to be 1.1 times 10 to the negative 10. Let's calculate QSP and compare it. So Q is calculated using the same thing, the product, so that in this case that's going to be barium times sulfate. And now we're going to plug in the concentrations of each here. Getting 6.4 times 10 to the negative 6. So everybody see how we calculated Q. Find the con. No, it's just like K, there's no units. So now that we have Q, we're going to compare it to K. So compared to K, is Q smaller or bigger? Q is bigger. So if QSP is bigger than KSP, does the solution precipitate or not? Yes or no?
Yes.
Yes. Back here. Q is bigger than K, the solution precipitates. So in this case, our solution is barium sulfate. Barium sulfate precipitates. So for these problems, use the dilution equation to find what the concentration is of each of your ions, and then plug it into Q equation compared to K. K again found in that table on page 803. Now, for part B, we're not going to do it in its entirety just because of time's sake, but take note in part B, let me just erase this. No, I'll erase all of it. No, I don't think it will let me. There you go. So in part B, what would be the product that is going to precipitate out, again, when we react potassium sulfate with now silver nitrate? Silver sulfate. What is the formula for silver sulfate? What's the ratio of silver to sulfate? Is it 1 to 1? No, it's 2 to 1. It's 2 to 1. Which means when I write out the equilibrium expression for that, silver sulfate is going to make 2 silver ions. That's just a plus, 2 plus. And a sulfate ion. Which means when I write the formula for Q, Q is going to be equal to the concentration of silver. What special do I do there? Squared, good. Squared times sulfate. So don't skip writing out your dissociation equation, because we need to make sure that we know its stoichiometry, because the stoichiometry is going to affect how we calculate Q. Make sense? Do you need to do that one in entirety, or do we feel like we can do it entirely? Let's do that one entirety. Okay. So same thing, we're going to determine what the concentration is of the silver ions and the sulfate ions using the dilution equation. So first of all, let's determine the concentration of silver ions using M1V1 is equal to M2V2. So M1 is that 0.15, V1 is the 175. Is equal to M2, that's what we're finding, times V2. What's our final volume going to be here? $825. So we started with 650 and we've added 175, so $825. So our molarity of silver is going to be plug this in wrong. .032. M2, which is our silver. So that's what goes in here. All right. Do the same thing for the sulfate ion. So for the sulfate ion, M1 is going to be 0.0080, V1 is going to be the 650, and V2 is going to be, again, the 825. For sulfate, M1 is 0.0080. So what's the concentration of sulfate that goes in here? What's the concentration of sulfate? Good, 0.0063. 0.63. Plug it into our equation, calculate Q, 0.032 squared times 0.0063. 6.45 times 10 to the negative 6. Now, KSP for silver sulfate, we look at the table, is 1.5 times 10 to the negative 5th. So compared to K, is Q smaller or bigger? Smaller. Q is smaller than K, so does the solution precipitate? No. Q is less than K, so no precipitation. Feel better about that kind of problem? All right. Let's move on to the next section. Common ion effect. Where have we heard about common ion effect before? It was the title of the very first section of the chapter. No, that was a full week ago, right? All right, so common ion effect, we use the beginning of the chapter with acids and bases to determine buffers. So we had a weak acid plus a salt containing its conjugate. So the conjugate that came from the salt is part of the equilibrium expression for our weak acid. Therefore, we had both starting amounts of our weak acid and starting amounts of one of the products, in that case our conjugate. We can do the exact same thing with solubility expressions, and once again, it's going to be an ice table to solve it. All right. So we know that in a saturated solution of a compound, we can determine its solubility just using an ice table and its KSP. So, for example, we could find that for for a saturated solution of silver chloride, the solubility is going to be 1.3 times 10 to the negative fifth molar, and that's going to be at the concentration of the silver ion. When we did those ice tables, we were starting with 0 for both of our ions because we were starting with pure water and dissolving silver chloride into pure water. Therefore, 0 on the top of both ice tables. However, what if instead of trying to dissolve this in pure water, we try and dissolve it in a solution of silver nitrate? So now we're trying to dissolve silver chloride in a 0.1 molar solution of silver nitrate. Well, the problem is 0.1 molar solution of silver nitrate has what concentration of silver ion already in it? 0.1 molar. Which means when we do our ice table, our initial concentration of silver ion is going to be 0.1 molar. So that will change the end result. Now, when we do our ice table, we have to consider that silver starting at 0.1 molar, which will change its equilibrium concentration. So now this 0.10 plus S, this is coming from the very bottom of the ice table. Again, silver chloride in equilibrium with silver ion plus chloride ion. So now we're starting with 0.1 molar, nothing of that, plus S, so our equilibrium is 0.10 plus S and S in our ice table. And again, we ignore that because it's solid. So that's where the 0.1 S times S comes from. Silver ion times chloride ion. Silver ion is 0.10 plus S, and then the chloride ion is just S. So now at this point, we can plug it in, solve for S using KSP, which we got from the table. Issue is, of course, whenever we have a plus S, then we're going to be dealing with the quadratic equation. To avoid the quadratic equation, we usually made the assumption that X was small, which was a fair assumption as long as K was relatively small. Luckily for us, all of the K values in our solubility table are all very small Ks. So this is going to be a safe assumption to make for this section. So if we assume S is small, then we can kind of ignore this plus S and just say 0.1 molar. So we're just going to ignore this plus S. So now KSP is just going to be equal to 0.10 times S. Now KSP for the silver chloride, again from the table, 1.6 times 10 to the negative 10. Solve for S, we find that S is now 1.6 times 10 to the negative molar. In the pure water solution, we got that S was 1.3 times 10 to the negative fifth molar. So what happened? Did it go up or down? Did our solubility increase or decrease? Remember, S for pure water was 1.3 times 10 to the negative fifth. S in the silver nitrate solution is 1.6 times 10 to the negative 9. So did my solubility increase or decrease? Decreased quite a bit. So by trying to dissolve silver chloride in a solution that had a common ion, it significantly decreased the solubility. Because basically what we're doing is in our equilibrium expression, I lost my G there, by adding silver nitrate, we were increasing the amount of one of the products. According to Le Chatelier, if we add some product, that's going to drive the reaction which way, forward or backwards? Backwards. So if we drive the product or the reaction backwards, that's back to the reactant, which is the solid. So less will dissolve. We'll have more solid and less that was dissolved. All right, let's try this out. Calculate the molar solubility of silver chloride in a solution that is 6.5 times 10 to the negative third molar silver nitrate. From the table on page 803, KSP for silver chloride is 1.6 times 10 to the negative 10, and that's from the table on page 803. So we're going to do an ice table. First part of the ice table is writing that equilibrium expression. So the equilibrium expression for silver chloride turns into silver ions and chloride ions, ignoring our reactant because it's a solid. Now, our initial concentration of silver ion is coming from the silver nitrate. If I'm 6.5 times 10 to the negative 3 molar silver nitrate is AgNO3, then, because it's 1-to-1, I am 6.5 times 10 to the negative 3 molar silver ion. Pay attention to the stoichiometry there. There it was 1-to-1, but it might not necessarily be 1-to-1. So that's our initial concentration of silver, which is what goes in right here to our ice table. Chloride starting with 0, plus S plus S. Now we plug that in here, 6.5 times 10 to the negative 3rd plus S for silver, and then just S for chlorine. To make our math easier, and we assume S is small, we're going to ignore that plus S. So 1.6 times 10 to the negative 10 is equal to 6.5 times 10 to the negative 3rd. Ignoring the plus S, just times the S on the end. Okay, 2.5 times 10 to the negative 8. It's equal to S.
Where did that 6.510
That number?
No, 6.510 to the negative 10.
That from that number right there?
Oh, yeah. I thought it was 10. So what if it was like, if you were in, if the question was like in a solution that is 6.5 times in a negative 3rd in silver sulfate, where you have like silver squared.
Good, good. So if it was silver sulfate, all that would, well, silver sulfate's not soluble itself, but let's pretend it was. If it was something that had 2 silvers, then when we go from this step from here to here, we would have doubled its concentration. And so it would have doubled this number right here. Questions? All right, so one special case of common ion effect is where the common ion is either a hydrogen ion or a hydroxide ion. What's so important about that? Well, hydrogen ions and hydroxide ions are determined by the pH of the solution. So one way to push the solubility in one direction or another is by pushing the pH either up or down, because that will mess with the relative amounts of hydronium and hydroxide. So let's consider magnesium hydroxide. So magnesium hydroxide, according to our rules back in chapter 4, is generally insoluble. But we do have a KSP value listed for it. The KSP value for magnesium hydroxide from page 803 is 1.2 times 10 to the negative 11. So we can determine its solubility. So we made 2 hydroxides, so that means our hydroxide is going to be squared. It also means in our ice table we're going to end up with plus 2s. So that's where the 4s squared came from. We did this one earlier, didn't we? We got 4s squared, cubed. Divide both sides by the 4 and then cube root of both sides to find the solubility is 1.4 times 10 to the negative 4th molar, right? So again, that's in pure water. Now, if I change the pH, that's going to mess with hydroxide. So instead of saying I'm dissolving it in a solution that already contains this particular ion, we can talk about it in terms of the pH. So the hydroxide ion concentration there, if we just wanted to know what the pH of this concentrated solution would be, we would take our S, our solubility, plug it back in here. So 2 times S will give us our concentration of hydroxide. Again, that's concentration of hydroxide there, and that was the magnesium. So 1.4 times 10 to the negative 4th is our S, times 2 gives us a hydroxide ion concentration of 2.8 times 10 to the negative 4th. Take the negative log of that. That gives us a pOH value, subtracted from 14. That tells us the pH of this solution is 10.45. So if I take magnesium hydroxide and I dissolve it in pure water until it is at its maximum solubility or saturated solution, that solution would have a pH of 10.45. Now, if I started off, instead of putting this in pure water, I put in a solution with a pH less than 10.5, then if I lower the pH, what is that doing to the hydroxide? Is that increasing the hydroxide or decreasing the hydroxide? If I lower the pH, that means hydroxide is what, more or less? Less. Lowering pH, because remember, hydroxide is a base. Bases are high in pH. If I lower the pH, I'm making it more acidic, which means I'm making less hydroxide. If I decrease the amount of hydroxide, according to Le Chatelier's principle, which way will the reaction run, forward or backward? Forward. So if I run the reaction forward, is that dissolving more or dissolving less? Dissolving more. Therefore, if I lower the pH, have a pH less than the starting pH, then the solubility will increase because I'll be driving the reaction forward by removing hydroxide. What would happen if I put it in a solution that had a pH greater than 10.45? Good. The opposite would happen. Solubility would decrease. Okay, so that one was pretty obvious because it actually contained hydroxide. Let's do one that doesn't contain hydroxide or hydronium but would still be affected by pH. Let's look at barium fluoride. Barium fluoride, according to the rules in chapter 4, again, generally insoluble, but it does have a KSP value in the table. And barium fluoride has a KSP value of 1.7 times 10 to the negative 6. Again, from the table on page 803. Now, it doesn't seem to contain, if I look at barium fluoride, it doesn't contain hydroxide, it doesn't contain hydronium, but fluoride. Fluoride, is that a neutral salt? Salts that contain fluoride, are they neutral, acidic, or basic? All right, so fluoride is the conjugate of what, an acid or a base? An acid. I can add hydrogen, but I can't take hydrogen away. So if I added hydrogen, what have I made? Good. Hydrofluoric acid. Strong acid or weak acid? Weak acid, which makes F minus a what? Good, strong conjugate base. Base. Doo-doo. If I put this into an acidic solution, that acidic solution contains hydronium. Hydronium will react with fluoride to make HF. If I lower the pH, what does that do to the hydronium? Make more hydronium or less hydronium? More hydronium. Lowering the pH means I have more hydronium. If I have more hydronium, which way is this reaction going to run? Forward or backwards? Backwards, which means what's going to happen to the fluoride? Am I making more fluoride or less fluoride? Less fluoride. So that is going to consume those fluoride ions. So if it consumes the fluoride ions now I'm decreasing the amount of fluoride. So back to my equilibrium for the barium fluoride, now I'm decreasing the amount of fluoride. If I decrease the amount of fluoride, is the reaction going to run more forward or more backwards? More forward. So is more going to dissolve or less going to dissolve? More will dissolve. More will dissolve. The reason why more dissolved in an acidic environment is the acidic environment increased amount of hydronium, and hydronium was consuming fluoride to make hydrofluoric acid. So the acid consumed some of the product, consumed some of the fluoride ion. By consuming some of that fluoride ion, it decreased it. Decreasing it drove the reaction forward, which dissolved more of our barium fluoride. So solubility will increase in the acidic solution for a salt that contains a strong conjugate base. Now, of course, if the salt contains a conjugate of a strong acid, such as chloride, bromide, or nitrate, it's not going to be affected by the pH at all, because those are weak conjugate bases. Let's try reasoning through a couple of these. Which of the following compounds will be more soluble in an acidic solution than in water? So the first one is copper sulfide. Copper sulfide. So sulfide here. Sulfide is the conjugate of what acid? I know, we talk about 3 different acids that contain sulfur. We're like, oh my gosh. We have sulfuric acid, sulfurous acid, and hydrosulfurous acid. Woo! And only one of these is strong. Sulfurous. I don't know if I spelled that right, but acid, sure. What's the formula for sulfuric acid? Good, H2SO4. What's the formula for sulfurous acid? H2SO3. What's the formula for hydrosulfurous acid? H2S. All right. So sulfide is the conjugate of which one of these? H2S. It's the conjugate of H2S. Hydrosulfurous. Is that a strong acid or a weak acid? Weak acid. So if this is a weak acid, then sulfide is a what conjugate base? Strong conjugate base. So we're back to the exact same situation we were in the last problem with the fluoride ion. So in the last problem with the fluoride ion, was its solubility increased in acidic solution or decreased? Increased. So it will increase the solubility in water.
So is it only if you have a weak, well,
But if you're the conjugate of a, such as here, silver chloride, chloride is the conjugate of a strong acid, so would it be affected by pH? No, so silver chloride will not be affected by pH. All right. So let's see here. We've got lab tomorrow, and your homework is due tomorrow. So see you guys tomorrow.